Good morning students. Today we are going to discuss about speed of sound. As you know very well, sound can travel through a medium like solid, liquid and gas. But speed of sound will not be similar in all the three medium. Let us know the definition for speed of sound. As you know very well, speed is equal to distance by time taken. Right? Here we are going to discuss about speed of sound. We are going to add only one word here, that is distance travelled by a sound wave, because we are discussing about sound. So here distance travelled by a sound wave. Divided by time taken. That's all. So distance travelled by a sound wave by time taken. Per second, how much distance is travelled, that is called as speed of sound. So I can write this speed is equal to distance travelled by a sound wave. One sound wave, it's nothing but wavelength, right? So one wavelength divided by same time taken. So here wavelength we know it is denoted as lambda, time taken is nothing but t, speed is nothing but v. So as you know very well, n is equal to frequency is nothing but 1 by t. You just substitute this, so v is equal to lambda. So this one we can write like this so that you can easily understand. So lambda into 1 by t. So instead of 1 by t I can write lambda into n. So v is equal to n lambda. So, speed of sound can be measured when you know the value of one wavelength and frequency. So, product of wavelength and frequency is called as speed of sound. Okay, next we are going to solve with a problem. So, once again I repeat this. Speed of sound is nothing but distance travelled by a sound wave per second. As you know very well, speed is equal to distance by time taken. Here we are going to discuss about sound wave. So we have to add only one word, that is distance travelled by a sound wave by time taken. So speed is equal to distance travelled by sound wave is nothing but one wavelength. For example, it will be like this. So this is called one wavelength, lambda. So the wavelength that should be taken as lambda divided by time taken is nothing but t. So lambda by t. This can be written like this, lambda into 1 by t. So as you know very well, n is equal to 1 by t, the formula. So v, just substitute v is equal to lambda into n. So when you know the value of lambda and frequency, which means wavelength and frequency, we can easily find out speed of sound. Let's solve one problem. A sound wave has a frequency of 2 kilohertz. 2 kilohertz. Unit of frequency is hertz, so it's given n value is given here. So 2 kilohertz, kilo means 10 power 3, which means you have to multiply with 1000, and wavelength of 15 centimeter. Wavelength is nothing but lambda. How much time will it take to travel? They are asking you to find out time will be taken. How much time is taken to travel? 1.5 kilometer. So here is given directly n is equal to 2 kilohertz, that should be converted into hertz. So 2 into 1000, 2000, then lambda is equal to 15 centimeter, that should be converted to meter, that is 0.15 meter. So what we have to find out? V. V we know very well, V is equal to n into lambda. So we know V is equal to n into lambda. Then here they ask you to find out t value. What is the t? Is nothing but time. So here I need to find out time. So what should I do? Time is equal to, time should be taken this side. So sound will come here. So t is equal to, means time is equal to, time I need to find out, speed will come down. So down, distance by speed. That's it. So we know the formula 1 and formula 2. First I need to find out V. V is equal to n value 2000 into 0.15 meter. So V is equal to these two, you get 300 meter per second. So now we know the value for V. Then we have the value time is equal to distance, how much? That is 1.5 kilometers. So 1500 meter divided by speed we have found, that is 300. That 2 you have to cancel. Seconds. So time taken is 5 seconds. That's it. Now we are going to discuss about speed of sound in different media. As you know very well, sound will travel through a medium, but speed will not be similar in all the three: solid, liquid and gases. For example, speed will be maximum in solid, then liquid, then air, which means gas. So here we are going to discuss speed of sound in different media. For example, air. At 30 degrees Celsius, the speed will be 330 meter per second. At 25 degrees Celsius, 340 meter per second. So when temperature increase, speed will increase. When temperature decrease, speed will decrease. So based on that, speed of sound in different media, for example, steel, 5960 meter per second. So water, which means sea water, that is 1531, and 340 meter per second. So here we can easily understand that solid has the greater value speed, then liquid, then air, gas. So solid has greater value, liquid and gas.
What about the speed of sound though? How fast can it travel?
Comparatively speaking, the speed of sound is less than that of light. If you notice, on stormy days, we see the lightning first and then hear the thunder. That's because light travels faster than sound, and so lightning reaches us first. Speed is the ratio of unit distance to unit time. For a sound wave, the unit distance is its wavelength, lambda. And the unit time is the time period, t. Therefore, the speed of a sound wave is the ratio of its wavelength to its time period. It is denoted by the alphabet V. You know that the reciprocal of a time period of a sound wave is equal to its frequency. Therefore, the speed of a sound wave is the product of its frequency n and wavelength lambda.
What about the speed of sound in a medium other than air?
Well, that differs from medium to medium. The speed of sound depends on the properties of the medium through which it propagates. The important properties that affect the speed of sound are the temperature and the density of the medium. If the temperature of a gas increases, its density decreases, resulting in an increase in the speed of sound and vice versa. The speed of sound in various media at specific temperatures is given in the table. From this table, you can see that sound waves propagate faster in solids than in liquids and gases.
And what happens when an object is moving faster than sound can move in that medium?
Very good question. Have you ever heard of sonic booms? When an object is traveling at a speed greater than the speed of sound in air, it is said to be at a supersonic speed. For example, a bullet fired from a gun travels at a supersonic speed. Some jet aircrafts, at times, travel at supersonic speeds. When an object, like a jet aircraft, travels at supersonic speed, It produces shock waves in the surrounding air. These waves carry enormous energy.
Now we are going to discuss about reflection of sound. What is reflection? Reflection is nothing but bouncing back. For example, I just take a ball and throw it on the wall. It will hit on the wall and reflect back. You just take the same ball and throw it on the pillow or a bed. Will it reflect back? No. Some object will reflect, some object will observe. So when we pass sound in a particular room, all the sound will not be reflected. Some sound will be reflected, some sound will be observed. So based on the property that you use, which means based on the object that we use, that objects will absorb. For example, the wall will reflect easily and the curtains and other bag and some other objects will absorb the sound. So here we are going to discuss about reflection of sound. We have two laws, that is law 1 and law 2 for reflection of sound. For example, I have taken a small surface. I just send a sound wave. This is called incident wave, that is I. After hitting on the wall, it will reflect. This is called reflected wave, that is R. So this is incident wave, this is reflected wave, this is called point of incidence. Where the 2 points are meeting is called as point of incidence, that is O. Now I need to measure the angle of I, which means incident angle I need to measure. So what I have to do, I have to draw a perpendicular line. Perpendicular line should be drawn, that is called as normal. What is the use of the normal? We can easily measure the angle of I and angle of R. The distance between I and the normal is called as angle of incidence. The distance between normal to reflected wave is called as angle of reflection. So this is I and this is R. So it's very easy to find out the first law, that is I is equal to R. So angle of incidence is equal to angle of reflection. For example, when angle of incidence is equal to 30 degree, angle of reflection also should be 30 degree. So what is the use of this? When we get the reflected sound in the same angle, which means incident angle and reflected angle is same, we can hear a clear sound. If the angle is changing, for example, incident wave is 30 degree and reflected wave is 40 degree, we are not able to get a clear sound. When we have an equal value, which means I is equal to 30, R is equal to 30, or I is equal to 40, R is equal to 40, we can hear clear sound. That is the first law. So incident wave is equal to reflected wave. Second law is very simple. Incident wave, reflected wave and normal are in the same plane. So this is incident wave, this is reflected wave and normal will lie on the same plane. Is called as second law of reflection. So once again I repeat, we have two laws of reflection. First one is incident angle should be equal to reflected angle. So which means angle of incidence is equal to angle of reflection. So I is equal to R. When I is equal to 30 degree, R is equal to 30, or when I is equal to 40 degree, R should be 40 degree, so that we can get clear sound. Second law, that is incident wave, reflected wave and normal are in the same plane. So incident wave, reflected wave, normal are lying in the same plane. After having learned law 1 and law 2, we know the uses of reflection. So when we have reflection, we can hear the sound. So this application will be used in the musical instruments. For example, megaphone or loudspeaker. So why we are using all that? For example, in a traffic, we can see that policeman using a speaker to clear the crowd. So these instruments will be used working on the reflection of sound. When we have multiple reflection, it will travel to a long distance. For example, Nadaswaram. We can see a long conical pipe which will be used for traveling sound for long distance. Scope is an instrument used to find out the heartbeat, right? So how it is working is because of multiple reflection will take place in the tube, connecting tube. So this is the main use of reflection of sound.
Look at this ball. When it is thrown on a hard surface, it bounces back. Light as well as sound waves behave in a similar manner. When light rays are incident on a reflecting surface, they bounce back. Similarly, a sound wave incident on a hard surface bounces back into the same medium. This is known as the reflection of sound. According to the laws of reflection of sound, the direction in which that sound wave is incident and the direction in which it is reflected make equal angles with the normal to the reflecting surface at the point of incidence. The incident sound wave, the reflected wave, and the normal at the point of incidence are in the same plane. Sound waves need polished or rough surfaced obstacles to get reflected. Let's verify these laws through an experiment. To set up the experiment, we take two identical hollow pipes, PQ and RS, each about 2 feet long. We place these pipes on the surface of a table near a wall so that their axes intersect at point O on the wall as shown. Then, we keep a clock near the end P of the pipe. Finally, keep a cardboard vertically in between the pipes, so that the sound of the clock at P cannot be heard directly at the end S of the pipe RS. Now we try to hear the sound of the clock from the end S of the pipe RS. The angle of the pipe RS can be changed by tilting it in a horizontal plane about the point O. The sound is very feeble, isn't it? That's a little better. Wow, that's quite clear, right? Oh ho, this angle is not so good. The sound has become feeble again. A feeble ticking sound can be heard through the pipe RS in random positions. Fix the position of the pipe RS at the angle where the loudness of the sound heard is maximum. Let's now measure the angle between the axis of the pipe PQ and the normal to the wall at the point O. This is the angle of incidence, I, for the incident sound wave. Now, we'll measure the angle between the axis of the pipe, RS, and the normal to the wall at the point O. This is the angle of reflection, R, for the reflected sound wave. You can see that the angle of incidence is equal to the angle of reflection. Now, try changing the orientation of the pipe, RS, by tilting it vertically. The audibility, that is, the loudness of the reflected sound, decreases. This is because, when tilted vertically, the plane of the reflected sound wave is different from the plane of the incident sound wave. In this situation, only parts of the reflected sound wave pass through the pipe RS. This confirms that the incident wave, the reflected wave, and the normal all lie in the same plane.
Now we are going to discuss about echo. Echo is nothing but sound reproduced due to the reflection of original sound. For example, when we stand in an empty room or in front of a mountain or a big wall, you can get the reflected sound again. The same sound will be repeated. That is called as echo. So how we can define that is sound reproduced due to reflection of original sound. When we get the same sound again because of the reflection is called as echo. The sensation of sound persists in our brain for about 0.1 second, which means, for example, a man who is standing here and speaks, here we have a mountain or any wall. That sound, the reflected sound should be persist within a 0.1 second, so that we can get a clear echo. Otherwise, we are not able to get, which means the time interval between a man and the obstacle or an object should be 0.1 second, so that we can get a clear echo. Let us calculate what is the distance should be maintained a man and the object. What is the distance should be maintained to get a clear echo? For example, sound can travel through air, right? So at 25 degrees Celsius, sound can travel with speed 340 meter per second. 340 meter per second. So the sound that persists in our brain about 0.1 second. So time taken, that is 0.1 second. So when you multiply these two, we will get 340 into 0.1, that is 34 meters. So a man and the object, the distance between these two should be maintained, that is 34 meters. So the total distance is 34 meters, and the man to a wall, that should be 17 meters. Man to a wall, and the wall to a man, that should be 17 meters. So altogether we have 34 meters to get clear echo, right? So when we stand in front of an object and speak, the gap between the man and the object should be 17 meters. So the sound travels with 17 meters and reflect back with 17 meters, so that we can get a clear echo.
Let's now observe this boy shouting into a well.
This is an experiment.
Did you hear that? That was the boy's voice reflected back from the water in the well. In our daily lives, we call this sort of a reflection an echo. Thus, an echo is repetition of sound that results as a reflection from a surface. Here's an interesting fact about the origin of the word echo. According to Greek mythology, Echo was a nymph who had the job of talking incessantly to Hera, the queen of gods, so that her husband Zeus would not get caught in his misdeeds. Hera caught on to Echo's tricks and cursed her to only be able to say what others had just said. Thus, reflection of sound can be attributed to Echo talking under the curse, repeating what you say.
Hello!
You may be wondering why you don't hear an echo for reflection of every sound. To explain this, let's observe a scenario where a man standing in front of a cliff shouts, "Hello."
Hello! Hello!
Did you hear that? There was a clear echo. Now, let's see what happens if the man moves closer to the cliff and shouts, "Hello" again.
Hello!
In this case, there was no echo when the man shouted. Why do you think you could hear an echo in the first position but not in the second? Try and analyze what changed in the second situation. Nothing but the distance of the man from the cliff, right? It is the distance that is making a difference. We cannot hear an echo unless the reflecting surface is beyond a specified distance from the source of the sound. In this case, it was the man shouting hello. To find out how this works, let's examine how our brain processes sound. The sensation of sound persists in our brain for 0.1 second. Therefore, to identify an echo, the time interval between the reception of the original sound and the reflected sounds should be at least 0.1 second. So, how much distance do we need between the source of a sound and the reflecting surface to be sure that we will be able to hear an echo? Let's find out. The speed of sound at a given temperature say 22 degrees Celsius, is 344 meters per second. Consider the echo produced by shouting on a cliff. Let d be the distance between the source of sound, in this case, the man, and the obstacle, in this case, the cliff. The distance travelled by the sound wave from the source to the obstacle and back to the source is equal to 2d. To hear the echo, the duration in which the reflected sound travels back should be at least 0.1 second. Therefore, by using the expression of speed, the distance travelled by the sound wave is equal to the product of the speed of the sound and the time for which a sound persists in our brain. On substituting the values and simplifying, we get the distance is equal to 17.2 meters. Therefore, the minimum distance required to hear an echo is 17.2 meters. Note, this distance will change with the temperature of air, as the speed of sound changes with the temperature of air.
Reverberation. Reverberation is nothing but repeated reflection of sound. For example, when I am standing in a particular room, when I speak, when I play any audio, what will happen? It will reflect in various places and reach your ear. So what will happen here? We are not able to get a clear sound. That's called reverberation. So here the repeated reflection that result in persistence of sound. For example, in a particular hall, we have speaker and we have listener. When speaker speaks, that listener is not able to get the sound because due to the repeated reflection, the reflection is repeated, it hit on various places and reach the man. So that what will happen, he is not able to get a clear sound. How can we reduce the reverberation in a particular hall, theatre or auditorium? When we use sound observing material like cardboard, cushion seat, curtains, like this, right? So when we use all these sound observing material, we can reduce the reverberation.
When you hear thunder rolling, the sound continues for some time. The rolling of thunder is due to the successive reflections of sound from a number of reflecting surfaces, such as the clouds and land. This is called multiple reflection of sound. Thus, multiple reflection of sound is the successive reflection of sound from various reflecting surfaces. We find many useful applications of multiple reflections of sound in our daily life. A doctor using a stethoscope to give you a checkup is a very common sight. A stethoscope uses the principle of multi-reflections to help the doctor hear your heartbeat. Let's take a look at how it works. The chest piece of the stethoscope consists of a plastic disc called the diaphragm, which is placed on the patient's body. The sound of the heartbeat vibrates the disc. These vibrations produce pressure waves which travel to the listener's ears through the hollow tubes by a series of multiple reflections throughout the tubes. There are various other applications of multiple reflections. Megaphones, horns, and musical instruments like trumpets are designed to magnify amplitude of the sound and reflect and propagate sound waves in a particular direction. The curved ceilings of cinema halls and conference halls are also designed keeping the principles of multiple reflections in mind. The curve in the ceiling ensures that the sound is reflected to all the corners of the hall, so that there is an even distribution of sound. In some cases, a soundboard is positioned behind the stage so that the sound waves produced are spread across the hall evenly. However, in cases where these halls are not designed properly, multiple reflections can lead to uneven distribution of sound. Let's see what causes this problem. Consider a big closed room where a source S, a speaker, and an observer O are in the positions as shown. The observer may hear more than one reflection of sound produced by the source. This is due to the multiple reflections produced at different locations on the walls and in the room. This can make it difficult for the observer to focus on what the speaker is saying and hear him clearly. The reflected sound is heard until its intensity is reduced to a value where it is no longer audible. Finally, the sound fades off completely. Thus, the observer hears the sound produced by the source persistently till it fades away beyond audibility. This phenomenon of persistence of sound in a closed enclosure, due to the multiple reflections of sound in an enclosure, is called reverberation. Reverberation is generally minimized in auditoriums by covering the walls, the ceiling, and the flooring using sound-absorbent material like cardboard, thick curtains, and fiber.
Ultrasonic sound. We have three types of sound. One is audible sound, second one is ultrasonic sound, third one is infrasonic sound. So audible sound we know very well, a frequency between 20 Hz to 20,000 Hz. If it is below 20 Hz is called as infrasonic, above 20,000 Hz is called as ultrasonic sound. Now we are going to discuss about ultrasonic sound, that is frequency greater than 20,000 Hz is called as ultrasonic sound. This ultrasonic sound cannot be heard by the human being, but some animals can hear the ultrasonic sound. Let us see the applications of ultrasonic sound. First one is cleaning technology. The ultrasonic sound will be used in a cleaning technology to remove a minute particle which are present in the water path, right? Second one, detect cracks in a metal. So we can easily identify where there is a crack in a particular metal sheet, right? So when we pass an ultrasonic sound wave, it will easily find out where there is a crack. Third one, echocardiography. It's very, very important. Using the echocardiography method, we can find out the image of the heart. So various parts which are present there, we can take particular place where you want to take a picture. So using echocardiography, we can easily find out the image of a heart. Fourth one, very important, that is when you have a kidney stone formed, which means a stone formed in a kidney, we can easily break when we pass the ultrasonic sound. So what will happen? That kidney stone will be cut down in a small pieces and it will come out through the urine. So it is very easy method. So these are the important uses of ultrasonic sound. So mainly we are using in a medical field, that is echocardiography and remove a kidney stone. Next we are going to discuss about sonar. It is a very important application of ultrasonic sound wave. Sonar is nothing but sound navigation and ranging. Sound navigation and ranging is called as sonar. So mainly it will be used in boats and ships, right? So sonar is nothing but sound navigation and ranging is very important objective. Sound navigation and ranging. Let us see what are present in a sonar. Okay, first main purpose of using sonar is to find the direction, distance of the object and the speed of the object which are present in the sea. So we can easily measure when we use sonar the direction of the object, distance between the ship and the object, and the speed of the object which are traveling like whale and other animals which are present in the sea, we can measure. Second one is a transmitter and detector will be used. So this is transmitter, for example this is detector. So transmitter and detector will be used in a ship. So what is the use of transmitter? Transmitter will be producing the ultrasonic sound and transmit to the ground, which means it will transmit the sound. Ultrasonic sound can be passed into the water, right? So what will happen afterwards? That ultrasonic sound will hit on any seabed or any animals which are present or any obstacles which are present there, it will hit on the particular object and reflect back. That reflected waves will be collected by the detector. So what the use of detector is nothing but the detector will collect the sound back, right? So the reflected sound will be collected by the detector, and the detector will convert the ultrasonic sound into electrical signals, right? So this is the main purpose of transmitter and detector. So transmitter will produce ultrasonic sound and transmit into the water, and the reflected sound will be collected by the detector, and it will convert the ultrasonic sound into electrical signals, right? So what is the formula we will use here? That is speed is equal to, that is V is equal to 2D by G. V is nothing but speed, D is nothing but the distance. Why we have written that 2 is nothing but when I pass a sound wave, it will hit on a particular object and reflect back to the detector, right? So the distance, this is D and this is also D, so that should be added, right? So the distance should be added, that is 2D divided by, or you have to multiply with 2. For example, here we have 14, here we have 14, 14 plus 14, 28. So total distance is 28 meter. Time taken, how much time is taken to transmit and receive? Transmit and receive, we can calculate the total time. And V, the speed of ultrasonic sound. What is the speed of ultrasonic sound in water? That should be calculated. So based on the type of water, the speed may change. So we have to find out that, and we have to substitute in that formula so that we can easily find out. When you know the distance and time, we can find out the speed, or when you know the speed and the time, we can find out the distance. For example, I need to find out the distance. Very simple. I need to find 2D is equal to T, take this side, so V into T. So when you know the speed and the time, I can easily calculate the distance of the object which are present in the sea. Once again I repeat, sonar is nothing but sound navigation and ranging. It is used in the boats and ship. Here we are going, this sonar will be used in the purpose of finding the distance, direction and speed of underwater object. And we are using main instrument, that is transmitter and detector. Transmitter will produce ultrasonic sound and transmit into the water, and it will hit on any object which are present inside the water, and it will be collected by the detector. So ultrasonic sound will be collected back by the detector, and the ultrasonic sound will be converted into electrical signals. Then we have to find out the speed or distance or time based on the value which we have. For example, when I know the distance and the time, I can find out the speed, or I need to find out the distance, which means we need to find out the speed and the time. So when you know speed and time, I can calculate the distance. So D is equal to V into T by 2. So distance can be calculated. So this is very important application, will be used in boats and ships.
The human body. Even though we cannot hear them with our naked ears, ultrasonic sound waves have a wide range of applications in several fields, such as medicine and industry. For example, ultrasounds are used in a technique called echocardiography. This technique is used to diagnose any defects in the heart by obtaining the image of the heart. Ultrasonic waves are made to reflect from various parts of the heart, and the reflected waves form the image of the heart. Ultrasounds are also used for medical treatment. For example, it is used to help people suffering from kidney stones. Ultrasound waves are used to break the stones into fine grains so that they can be released from the body through the excretory system. In industrial applications, ultrasounds are generally used to clean parts located in hard-to-reach places. For example, in spiral tubes, odd-shaped parts, and electronic components. Here's how the cleaning is done. The relevant object is put in a cleaning solution, and these sound waves are sent into that solution. Due to the high frequency of the waves, the dust and dirt particles detach from the object, leaving it clean and dust-free. Ultrasounds can also be used to detect cracks and defects in metal blocks. Cracks or air bubbles present inside a metal block are invisible from the outside. To detect these cracks, ultrasonic waves are passed through the metal block, and detectors are placed on the other side of the block to detect the transmitted waves. On encountering a crack or an air bubble, the ultrasound gets reflected back, indicating the presence of the defect. Sonar stands for Sound, Navigation and Ranging. Sonar is a device that uses ultrasonic waves to measure the distance, direction and speed of underwater objects, or the depth of sea beds. It consists of a transmitter and a detector fitted at the bottom of a ship. Let's see how it works. The transmitter produces and transmits ultrasonic waves that travel through water and reflect back after striking objects or the seabed. The detector catches the reflected rays and converts the ultrasonic waves into electrical signals, which can be suitably interpreted. The distance of the object that reflected the sound wave is calculated using the speed of sound in water and the time interval between emission and reception of the ultrasound. This technique is useful in determining the depth of the sea and to locate underwater hills, valleys, submarines, icebergs and sunken ships. Let's consider an example where we use this technique to determine the depth of the sea. Let the distance from the ship to the seabed be d. The sound wave sent to the seabed has to travel twice the distance from the ship to the seabed. That is, from the transmitter to the seabed and back to the receiver. Twice the distance d is equal to the product of the speed of the sound wave in water, v, and the time interval between emission and reception of the ultrasound. Thus, the depth of the seabed is equal to half the product of speed of the sound and the time interval. Here is an example of a species that uses its personal sonar to obtain its food. A bat emits high-pitched ultrasonic squeaks that hit the obstacle or the prey and reflect back to the bat's ears. Based on the reflections received, the bat is able to determine the nature and location of its prey.
What is the use of ECG is nothing but if there is any variation in the heartbeat, we can find out the variation with the help of electrocardiogram. So for example, sound variation produced by the heart is converted into electrical signal. So if there is any variation in the heartbeat, that will be converted into electrical signal with the help of ECG. So as soon as we enter, if there is any emergency case, as soon as we enter into the hospital, first doctor will take the ECG, which means that heart variation. If there is any variation in the heartbeat, they will take as a printout and they will check the variations with the help of the printout. Okay, so the representation of the electrical activity of the heart muscles as it changes with the time. If there is any change in the heartbeat with respect to the time, that signals will be stored in the computer. So finally we can take a printout and we can check the heartbeat rate. That is a important use of ECG that you will study in a higher classes. So what is ECG is nothing but electrocardiogram. It will be used for finding the variation in the heartbeat that will be converted into electrical signals. That electrical signals will be stored in the computer so that we can take printout and see the variation in the sheets, so that we can easily find out what is the change in the heartbeat variations. We are able to hear a sound with the help of sensitive device is called as hear. For example, human here can hear the sound frequency range that is 20 Hz to 20,000 Hz. So when audible frequency is converted into electrical signals that travel to brain via auditory nerve, right? So that audible frequency is converted into electrical signal so that we can hear the sound. Let us see the structure and the functions of human ear with a video.
The human ear. The ear converts audible sound waves in air into electric impulses that reach the brain, enabling us to hear. Here, you can see the structure of the human ear. The human ear is categorized into three main parts: the outer ear, middle ear, and the inner ear. Let's see how these parts work together to produce the sensation of hearing. The outer ear, called the pinna, allows sound waves to pass into the ear through the auditory canal. At the end of this canal is the eardrum or the tympanic membrane. When a compression or rarefaction reaches the eardrum, it pushes or pulls the eardrum inward or outward respectively due to the pressure on the outer side of the membrane. The middle ear is comprised of three bones: the hammer, anvil, and the stirrup. These bones amplify the vibration and transmit the pressure variations of the sound waves to the inner ear. The inner ear is comprised of various parts, including the cochlea and an auditory nerve. The cochlea converts the pressure variations into electrical signals. Then, these signals are transmitted to the brain through the auditory nerve. These electrical signals are interpreted by the brain as the appropriate kind of sound. Hearing aids help us compensate for any shortcomings in our hearing capabilities. So, how does a hearing aid work? A hearing aid is a battery-operated device that receives sound waves through a microphone. This microphone converts sound waves into electrical signals, which are amplified by an amplifier. The amplified signals are sent to the speaker of the hearing aid. The speaker converts them into sound waves and sends them into the ear at a volume that the ear can clearly hear.